Hello, everybody. Good afternoon. Thank you so much for joining us here today. My name is Paula Basili, and I lead up communications efforts at the Center for Geospatial Solutions. And I'm very excited to be joined today by Max Burnett and Dr. Alejandra Botero-Acosta for October's issue of our bi-monthly Internet of Water Coalition webinar series. So Max Burnett and Dr. Acosta are here to present on the Great Lakes to Gulf Virtual Observatory. But before we get started diving into that awesome tool, I'd just like to cover a couple of small housekeeping items for today's webinar. So first, you'll notice that we are recording the webinar today. So if you are interested in revisiting any of the content, including the recording of this presentation and the slides, or in sharing it with any of your colleagues or friends, you can refer back to the Internet of Water website in about a week or so, where the recording and the slides will be posted for your use and for your reference. Second, we'll also be taking questions throughout the webinar and saving them for the end of the discussion. So if a question does pop into mind for you, feel free to jot it down in the Q&A portion of the Zoom window. We will be using the chat function exclusively to troubleshoot any technical issues that folks might be facing. So please note your questions in the Q&A and we'll go over them at the end of this presentation. And so lastly, again, if you do have any technical issues, like I said, feel free to put those in the chat, or if you're actually having trouble accessing the chat, our team is always available at the email address noted here to help troubleshoot. Okay. So now on to the main event. Like I said, I am pleased to welcome Max Burnett. Max is a full stack developer who has been developing data pipelines and web portals at NCSA for over 8 years. And his work has supported a variety of research projects in domains including nutrient conservation, digital agriculture, phenotyping, and data management. And with us today is also his colleague, Dr. Alejandra Botero-Acosta. Dr. Acosta received her master's degree in water resources from Universidad Nacional de Colombia and her doctoral degree in agricultural and biological engineering with a computer science concentration from the University of Illinois. Her research focuses on the study of the impacts of natural and anthropogenic stressors over soil and water resources at a watershed scale. And so we're very excited to have them join us and to also have all of you join us today virtually as well for this great discussion. So with that, we're going to get started. Max, I believe I'm handing things over to you.
Yes, thank you. And thank you everyone for having me. So as you might have gotten the impression from that introduction, I'll be starting off by talking a little bit about our web portal itself, kind of a little bit of the technology behind it and what you can see on our web presence. And then Alejandra will talk a little bit about some of the interesting analysis and science that's going on as part of this project. So again, I'm at the National Center for Supercomputing Applications at the University of Illinois, and for over, I don't know, almost 10 years now, we've been building web portals as part of the Great Lakes to Gulf project. So this is focused on the Mississippi River Basin, and it's focused on a network of data sources, including like sensors and streams and various types of official data sources, in order to provide kind of a comprehensive visualization and data exploration portal. So I'm going to talk again just a little bit about our front end, and then Alejandro will talk a little bit about our nutrient trend analysis. And so in terms of this virtual observatory that we have, it's primarily a geospatial application. It's an interactive tool. I'll demo it in just a few minutes briefly. And we have a number of different data layers that we bring in that you can overlay and kind of compare different data sources together. We bring data from NOAA, from USGS, from the EPA, a Water Quality Monitoring Council, and several other state level portals to kind of have what we think is a very comprehensive view focused on the flow of nutrients, kind of trends over time, sources of pollution, sources of management practices, and how that affects the landscape and how that affects the nutrient landscape. So this is what we'll see kind of demoed in a few minutes, but in terms of the broad swath of data sources that we have, I mentioned the National Water Information System super gauges. We have some of the water quality information portal sites from the US EPA. We have some information from NOAA and the Upper Mississippi Resource Monitoring Program. NGREC's Great Rivers Ecological Observatory Network, what we call GREON, has a number of buoys that are collecting information over time. And then we have some more kind of localized data sources as well. And we also have the ability to overlay data. So again, I don't want to belabor this too much, but in addition to these point sources where we can look at observations over time of nutrient and different water quality observations, we can also overlay these with some of these contextual layers. So we've brought in data from USGS's Sparrow model that looks at nutrient and phosphorus load. We've got some information on hypoxia extents in the actual Gulf, like polygons where you can see the hypoxia extent in different parts of the Gulf. We have some like land use layers, crop use from Cropscape. Hopefully I'm still coming through. It's telling me my internet connection is unstable. Nitrogen point sources and so on. And then we have information about green infrastructure. So this is primarily in the Chicagoland area. We can see some green infrastructure installations and things like that. And then finally, some of the newer data that we've added in recent months, there's been some interesting work from Dr. Kai-Yu Guan here at the University of Illinois, looking at the impact of cover crops like crop rotation and corn fraction, along with tile drainage to look at nutrient concentrations over time. And there's also some nitrate loading predictions at the Huck 8 level that we have brought in. And so with all these different data sources, we try to provide citations. You can see a citation there that we can also see on the website. And then we have some new data that's kind of covering agricultural conservation practices. So this is kind of a whirlwind of a lot of different data layers, but what I really wanted to show was the live demo portion of this, which is our website itself. So right now, any of you can go to greatlakestogulf.org and you can see our web portal. This is our landing page where we have obviously news, things like that. We also have some links to our state portals. So we have the main web application that I'll show in a minute, which has data all along the Mississippi River across multiple states. And we've also been working with different state agencies over the last year or so to build some of these bespoke state portals for different states. And in some cases, there are states that have existing monitoring sites that we were able to link to, like in Iowa's case. But in other cases, like Arkansas, we worked with the water quality monitoring team in Arkansas to identify their network of monitoring systems and bring in information about their Huck level trend analysis that they've performed. This is just one state's example. They have a tier system to their monitoring, so you can look at what their tier 1 sites are. You can also look at the full set of the water quality monitoring sites with, kind of visualizations based on how much data is available. We can click on one of these and actually see the history of observations. So this is one of our state portals, and we've been building these with multiple states. But we also have I think the most interesting is our GeoStreaming app. So if you click at the top under Explore, you can see a little bit of what you just saw previewed in the slide deck, where there are a number of data layers that you can visualize at the same time. What you see by default is our network of monitoring sites we've brought in data for, and I think almost all of them have more than 5 years of data available. If I turn off the clustering, you can kind of see the scope of the different networks that we have. And you can also open up the Sources tab to see groups of what these come from. So for example, if we look at the Grion buoys that I mentioned before, and if I click on one of these, we'll zoom right to that particular location. This one happens to be in Lake Decatur. Oh, and I actually see that this has data from today. So you can go ahead and click on any of these buoys. You can view the data, and now we can see here's the parameters that this particular buoy is collecting. We can see the observations from 2021 up until today. This is by month here. And you basically see everything that this buoy has to offer. In addition to that, we have the layers that you can overlay. So for example, this is Sparrow nitrogen load. If we look at that model, you can see the legend, you can see what that is. And you can ideally explore particular areas of interest to see what the historical monitoring information was, along with any other information layers that you've loaded in. And you can kind of explore and see a large amount of data that we've brought in. So again, we've been collecting data from a number of sources and working with a number of different agencies to try to build this system and continue to improve it over time. We constantly have new data flowing into the system, and we're building new dashboards. There's a couple of states that are going to be coming online in the near future, and additional ones that we're hoping to work with that are part of the hypoxia task force. So this list is going to grow, and I would encourage everyone to feel free to come here and explore these dashboards. And at the QA portion, at the end of this, you can ask questions about particular data sources or interactions. The best management practices dashboards, some of these other summary dashboards that we have. There's a lot of great information to look at and a lot of stuff to soak in. So I would encourage everybody to take a look at that and give us your feedback, because we'd love to get feedback from the community and get some advice on what we think could be added to this to provide additional value. And I think with that, Alejandra, I will pass it to you.
Thank you, Max. Good afternoon, everyone. I'm Alejandra Botero-Acosta, and I joined the Great Lakes to Gulf team to work on the trends analysis for the Mississippi River Basin. So initially, why did we decide to conduct this analysis? It's because we saw that multiple agencies at the federal and state level and some nonprofits were conducting trend analysis using different methods, data sources, and presenting the results in multiple ways. And given the importance that trends analysis has to analyze the impacts of nutrient reduction strategies in basins that go across state boundaries, we wanted to implement a unified analysis method over the whole Mississippi River Basin using the longest period of records available for this. So we started with a baseline of 1980 to 1996, and we found that very few sites had data before 1990. So we landed in a trends period of 1990 to 2020. Okay, so to conduct our analysis, we use the weighted regression on time, discharge, and season, better known as WRTDS. And this method implements the equation that you can see in this slide, which computes the concentration for every single day during the trend period using the time and discharge. And for this, we use 4 fitted coefficients that are calibrated for every single day using observed data that is close to the day we are simulating in discharge, in time, and in season. So as you can see, the main inputs for our method are observed concentration and observed discharge. And the model uses this data to calibrate and to estimate a concentration for those days that have missing data or missing records. So at the end, we'll end up with a continuous time series of concentration that we use later on to estimate or to compute the trends analysis. So for our observed concentration, we obtain the data from the water quality portal that holds data from USGS, EPA, and over 400 state, federal, tribal, and local agencies. So as you can see, this is a multi-source data set. Then they all use different sampling, different laboratory and reporting methods. So sometimes we have different reporting parameters that actually refer to the same one, different units, chemical forms, or different media. And regarding data quality, we'll also find duplicate records, sensor data, meaning that is left sensor when it's below the detection limit, or right sensor if it's above the calibration limit of the tool that they are using. There can be also negative, 0, or missing data in our time series. And for the stream flow, we use the USGA's National Water Information System that it holds data for over 1.5 million sites across the US. And this data set also has some data quality issues like missing, negative, and 0 records. And for our method for the WRTDS, we require a continuous data of stream flow in order to perform the analysis. We also need to use a stream flow and water quality sites that are co-located. And here I'm presenting 2 examples of sites that are actually co-located, but when we use the coordinates that are reported in the data set, they have different coordinates. So when we delineate the watersheds of each one of the sites, they look like they are not located at the same location. So we need to visually use satellite imagery to confirm this. This will take a good amount of time checking all the sites. Sorry. So as you can see, there are different issues for data quality. So we perform a data harmonization, which consists in create a quality control data set to use in the analysis. It requires using high quality level decisions to unify parameters that come from different data sources. So example of this is unifying collection organization names, unifying parameters name, unify units, unified fractionations, and synthesizing remark comments and codes. So when we perform the harmonization of our data set, we create new columns on our data set in case the user wants to go back and check the original data. They can perform corrections, or they can use the original data and instead of using the harmonized data set. In this slide, I am summarizing all the methods we use for the trends analysis. So initially we select the time period, then we create a consistent water quality data set from the multi-source data set, performing the harmonization of some parameters. Then we did a quality control of the data set by flagging outliers, duplicate records, sensor records, and then we conduct a site screening for those water quality sites that had more than 50% of sensor data. We didn't use those sites, for example. Then we did matching of stream flow and water quality sites using the COM ID, which is a ID number for every single segment of streams across the US. So those stream flow and water quality sites that had the same COM ID were matched, and then those matching pairs were screened for a quality control in the stream flow, having a 0, negative, and missing data. And finally, we did a screening of the matching pairs, making sure that we had water quality data on high flow dates, and also that the drainage area was a difference between stream flow and water quality watersheds were less than 10%. So when we had these matching pairs that comply with these requirements, we conduct the WRTDS method to have a continuous time series of concentration, and we analyze the significance of the trends analysis with a bootstrap method. So here I'm showing an example of the unification of the nitrogen parameter name. So we can see how in the left column we have the original characteristic name from the multi-source data set, and in the right column we have the harmonized unified characteristic name. So in our case, we decided to work with the nitrogen reported in milligrams per liter, and we decided to use this parameter because it's the most common form of nitrogen and is highly soluble. So here I'm showing the process of the matching of sites between stream flow and water quality. The blue points are all stream flow data from the USGS dataset, and the red points as the water quality sites. So after we perform the matching, we ended up with 408 matching sites, which are located in, which you can see in the map are the right side. After we had those 408 sites, we did a filter of sites with the following criteria. We selected those sites that had less than 50% left sensor data, that had quarterly sampling for at least 70% of the trend analysis, and that had water quality data for at least 10% of high flow days per decade. We also selected only sites that had stream flow site co-located, and we didn't use composite and field analyzed records. Composite means that those records that are collected during a 24-hour period. So with this criteria, we found out that 68 sites comply with all the requirements, and then we conducted the WRTDS. So those 68 sites were located, as you can see in the map in the left side here, and each single site has a different watershed associated to it, which are, you can observe here in the right map. So the WRTDS results of concentration were evaluated for performance using 3 different metrics. We used the extrapolation metric that compares the highest concentration between the observed and the simulated, the flux bias that tells us if the model is over or underestimating our concentration values. We use the Pearson correlation coefficient to estimate the linear relationship between observed and simulated. And finally, we did a visual inspection because the WRTDS model doesn't reproduce abrupt changes in concentration. It works better with gradual changes. So when there is a case of a site that has an abrupt change, the residuals would show a step change. And for those sites, it is advised to not use the results because the model might be providing anomalous estimates of concentration. So we removed those sites too. And after we have the continuous time series of concentration, we conducted a flow normalization of the concentration and the flux too. So what it does is removes the random noise of the flow that is introduced to our concentration and flux estimations. And it means that, well, it's the expected value of the concentration for every single time, and it's computed as the sum of estimate concentrations for every single day during our trend period, using all the flow that could occur for that day in the year. And it's multiplied by the probability of that flow occurring. And that probability is computed using the time series of flow that we are providing to the model. So as you can see in the examples that are here in this slide, the points are the original values, the original yearly values computed by the WRTDS model, and the line is the smooth flow normalized values. So the smoother values are the ones that we are using for our trends analysis. And to evaluate the significance of increasing or decreasing trends, we use the block bootstrap method. What it does is resamples multiple times, in this case it was 100 times, our records, and recomputes the WRTDS. And it estimates the fraction of replicates with a positive change. And that is related to the likelihood of an increasing trend in that site. So we performed this process for the original trend period, which was 1990 to 2020, and we did two more periods, two additional periods, 2000 to 2020, and 2010 to 2020. And we found different results for every period. For example, in Illinois, this site has a downward trend for the 10-year and the 20-year trend period, and no significant trend for the 2010 and 2020 period. In this second site located in Missouri, we found an increasing trend for the 30-year trend period, while it presented a decreasing trend for the 20-year trend period and an upward for the 10-year period. So we can see, depending on the period of time that we select for our analysis, we will find different results with a statistically significant result. One thing to mention here is that for this site specifically, the number of records is below 100, which can be considered not appropriate for a trends analysis. So some sites might not have enough data for computing a 10-year trend analysis. And this third site in Arkansas, we can see that it has increasing trends for the 30-year and the 20-year trend period, while the statistical test is telling us that it has a downward trend in the concentration, even though that we see that it looks like an increasing trend. However, this site has only 54 records for the analysis. So that indicate that it is recommended to use a good amount of years that have enough data, at least 100 records, to perform a trend analysis. So the next step for our trends is to compute the 90% confidence intervals to add the uncertainty of our estimations to our curves, and conduct the flow normalization using stationary and non-stationary flow assumptions, and further examine time periods and what is the impact of changing the period of analysis for different sites. We want to correlate also the significant trends with data that we already have in the Great Lakes to Gulf website, like conservation practices, dollars spent, and we want to do all for phosphorus too. One thing we also want to do for nitrogen is to try to increase the number of sites by using some of the sites that don't comply with all the requirements. For example, sites that have maybe 60% of quarterly coverage instead of 70%. We also want to use simulated streamflow data instead of observed streamflow data. And we want to use non-collocated streamflow gauges. For example, a streamflow that can be a few meters or kilometers downstream. Of course, we need to analyze what are the impacts on those before adding those sites. And here is an example of how additional sites could be located. For example, the red dots are sites that have more than 60% coverage, and the blue sites have more than 50% coverage. So these are sites that could be added if we relax a little bit our criteria. but we need to make sure that we are not adding too much uncertainty to our results. And so the lessons learned from this process is that quality of the data set evaluated by structure harmonization process is a key factor, that the methods and statistics used should be documented because they will impact the results that and the interpretation that we obtain from our trends analysis. Our results highlight the importance of long-term planning, for example, making sure that if there is a water quality network, that they are also performing a stream flow collection data in order to do a trends analysis in the future. And that we found that it's difficult to compare trend sites because although they look like a dot in a map, they actually are holding information from a whole watershed that is associated to that site. And they have different sites, different land uses, and different soils. So thank you so much. That's what I have. And I'm happy to answer any questions that you have.
Awesome. Thank you so much, Alejandra and Max, for that presentation. It's really exciting to see how a tool with especially so many different data layers has some really compelling applications. So really good stuff. So for everybody who's been tuning in, like I said, if you do have any questions for Alejandra or Max, please submit them into the Q&A. To kick things off, I actually do have a question of my own, and I think, Alejandra, this is for you. You know, I'm curious, you mentioned in your next steps wanting to bring in the use of a non-stationary flow normalization. Can you tell us a little bit more about, you know, that? What information will that kind of method provide that you're not getting now?
Yeah, so initially the WRTDS method was using a constant probability density function, meaning that it was assuming that the trends on the flow were going to be constant during the whole 30 years of the analysis. But with the non-stationarity, that means that we are adding the trends of the flow for the 30 years period, and we will be changing or updating our probability density function as we move in that trends period for the flow normalization.
Oh, interesting. So it sounds like it will be a much more kind of dynamic.
Yeah, we will be, it will let us like separate the trends of the flow from the trends of the source, in this case, nitrogen sources. So,
and how, because even thinking about the different location maps that you did show, how are you all thinking about adding in more water quality sites? What's the are there any set plans for that, or even how do you go about integrating those into this dashboard?
So for each one of the options, because we have multiple, one is relaxing our criteria and increasing the number of sites. The other one is using a hydrologic model for the streamflow data, or using streamflow data from non-collocated streamflow sites. For all of those, we will need to perform a sensitivity analysis, meaning taking one of the ideal sites and actually remove some of the records, for example, and then compare how the metrics will decrease as we do that reduction of samples. And with that, we can compute the uncertainty of just using some sites that doesn't have the 70% quarterly coverage.
I see. Okay. Max, I think this question is over to you, but can you talk a little bit more about the tech stack that's actually behind the site and what the development process overall was like? Would love to hear a bit more about that.
Sure. I'll share my screen again, because this is actually a good chance to talk about NCSA briefly. So everything that you saw on our dashboard, which includes the main dashboard with all that data, as well as our summary dashboard, which I didn't show much of, where you can see information on watersheds, you can see all this cool interactive stuff on the right-hand side. This is all driven by a piece of software that NCSA has developed for different projects over the, I don't know, last 10 or 15 years, called GeoDashboard. And this is an open source piece of software. So those of you who are interested, you can actually go to GitHub and deploy an instance of GeoDashboard on your own. GeoDashboard itself composes an API, which we have a PostGIS database for storing geospatial information. We have a GeoServer deployment where we store some of the geospatial layers Some of you may be familiar with this technology, where if we have some of these layers that are not point sources, but are in fact raster layers or imagery that we put to augment the map, that's in GeoServer. So we implement both of those technologies. And the actual geodashboard itself is a React application that's built of a bunch of different components, like the map component, the different visualizations that we use for the sidebar. So for people who, Great Lakes to Gulf is one project that's using this. There are others that are using this as well, like the state portals. These different components that you see on the right-hand side are generalized. So you have a data source and you have some graphs that you want to show, and then some association between the map and the sidebar. So for Great Lakes to Gulf, we can load all of these different sources of point information for nutrient and phosphorus, or for nitrogen and phosphorus. And then we can load the geospatial layers that show where those locations are and have a nice interaction between the map and the graph itself. So for GeoDashboard, if you were to deploy this, we basically have a configuration scheme that you can use to say, here's the layers I want to show. Here's my data sources, whether they are in a database, in a GeoServer instance, or in some cases, even just like a CSV file or a JSON file that you want to upload. And we can render all those things together. So then it's a matter of configuring these things in order to kind of define the layers that you want to show, all these things. And sorry, Ellen, who asked to see a little bit more of this. I know you asked one of those questions. There's a lot that you can play with on these applications. Like, what nutrients are we looking at? What years is the data that we're looking at correspond to? And some of these things are filtered based on when you select the geometries on the left-hand side. These are the type of dashboards that when I say we're building state dashboards, we have kind of a toolbox that we've built with GeoDashboard that we can build things like this. So the question is, what data do you have as an organization or a state portal? We can generally deal with a lot of different types of data, whether it's point sources of time series data, whether it's aggregate totals at the state level, the HUC level, some political boundary level, and what obviously the symbologies are and how those things interact. So for the state portals, it's been a process of asking what data they have, and then kind of sketching out some things that we would suggest visualizing and coming into a happy conclusion. So we would be thrilled to have GeoDashboard used in more contexts, and Great Lakes to Gulf as a project has been fantastic for helping GeoDashboard kind of push its boundaries as an open source project and add a lot more functionality thanks to Great Lakes to Gulf. But that's kind of the tech stack behind this. So, React and GeoDashboard, which has the PostGIS database, and GeoServer relying on this. And then OpenLayers is the map technology that we use with Vega as our charting library, if you really want to get into the details. And the last thing I'll add, just to respond to Ellen's question, who had asked a little bit more about data availability, because I probably didn't make this clear, that when you are looking at, for example, our data exploration portal, and you were to select one of these particular sites, the data that you access on our page, this one hasn't been updated in a few years, but you can download all this data. You download this, you can get it as a CSV. This is data that's coming from our GeoStreams API. We've got some of this in our database, or we're reading it from a source that we've loaded to the database in the past. So you can just download this as a CSV if you've sliced it in certain ways. And we are continuing to expand this at all times. Everything that Alejandra discussed today in terms of the trend analysis is going to land on this summary page very soon. We're actually just polishing this up as we speak. So you'll be able to come here and actually see the watershed that Alejandra showed, see the trend analysis, see what the results of the trend analysis were for the 10, 20, 30-year periods, and so on, as an additional kind of feature, and we'll continue to build that out. So hopefully that answers your question. Very
cool. And it sounds like a lot of good stuff to come. I'm curious, I think, especially watching through, watching the walkthrough, it strikes me that such a, simple but comprehensive interface can just is friendly to many different users, right? Obviously researchers like yourself, Alejandra, but also, environmental managers, community members, and others. And I guess I'm curious if you could talk a little bit about whether or not this tool was designed with a specific audience in mind. And then maybe too, I don't know if you have any kind of feedback to share from kind of the initial reception that you all have seen, any responses to date. Would love to understand that a little bit more too.
I can give my best swing at an answer, which, as someone who joined GLTG when it was already a fairly mature project, that originally the focus for Great Lakes to Gulf was to react to this nutrient pollution issue along the Mississippi River, and particularly tried to get quantifiable information collected from all these different data sources about cropping practices, the effect of different agricultural practices or tillage or those kind of things on the nutrient flows into the Gulf, and like hypoxia and some of the issues that can result from those shifting nutrient volumes. So originally the site was developed to try to work as a tool to support these groups that are doing research into issues like hypoxia, to collect the data from all these different groups in one place in order to give them maybe a centralized location where you can compare these different data sources. You can get information from, like USGS and EPA as two simple examples, have multiple programs that are complementary, but you might not discover them that way if you're relying on the government repositories of data. And one example that we've seen great reactions from the state portals is for the water quality portal data that I showed, like for Arkansas, for example, where I think everybody knows that data is available. And you go to the water quality portal, you can look up particular beacons, buoys, and get that information. But when you actually put it on a map and you can visualize the observations on a map in a time series plot, you start to be able to play games with the data that you can't really get a sense of if you're looking at it at a tabular level or at a base level. And so even things like the states themselves might not have a synoptic view of where are we collecting a lot of data and where are we not, and how much data have we collected historically and how much have we not collected as much over time. And so by playing games with how we symbolize these locations and how they're collecting data, we've actually gotten some interesting responses from the states seeing their data presented in a different way. So I think that the gist of it was primarily as a tool for assisting research and kind of teams that are trying to respond to this. And Ellen, thank you. She says it was designed for the general public to be able to use as well. So I should generalize this. The Walton Family Foundation, who I should have mentioned earlier, has funded this project. And so states and water quality managers are using some of the information to form their nutrient reduction plans. And if you look at those state portals, you'll actually see links to some of their nutrient reduction policies over the last few years and judge progress on that as well. Thank you, Ellen. Yeah, so I think it's kind of grown over time, which is fantastic. But originally, like a data access and education tool to support some of these programs.
Very cool. And last question, at least for me, although of course, if folks have any other questions, please again submit them in the Q&A. But I'm also just curious too, with so many different water quality data sources, how do you guys go about kind of quality assurance? What does that process look like? And is there anything you can speak to there?
It varies. So the simplest answer is, in most cases, until we get to the point where someone like Alejandra is trying to use the data, we try to not change it at all. So there actually are things in the data that won't surprise anyone, as far as surprising gaps in the data where maybe the sensor was down or the communication was interrupted. And there's not generally consistency about how no data values show up. So some data sources will be blank, or you'll see NaN or null or something more obvious that indicates or the dreaded -9999. Like there is kind of a translation sometimes to recognize those kinds of things with the data. But for the most part, we don't do much in the way of quality assurance. We simply try to cite the data that we got and point back to the source that we got it from, which, especially in these government sources, is already pretty well QA/QC'd before it gets to our servers. But in those cases, we generally just point to the policies of the data sources and try to the best that we can, make our users aware of gotchas in the data that almost got us. So if we understand that nitrogen is presented in these forms, don't confuse them. We'll just put, in some cases, citations on our site that say, note that nitrogen is shown in these forms, and try to warn the users, not to trip yourselves up, but we're not going to change the data in most of these cases, because we don't want to be authors of much of this. We want to be sort of the collators and faithful presenters. Yeah,
so really playing that, promoting that data discoverability role.
Yes, I will say, at the risk of maybe saying too much, is that We have had organizations that wanted us to show different types of trend analysis, like to have a big thumbs up or thumbs down, the nutrient trend is going up or down, that we did not feel comfortable with the lineage of the data, like basically how they calculated that answer, that we declined to show some of that data. So there's a little bit from our experts, you know, that are as part of the team to basically say, do we believe the science that went into this? And so in most cases, it's fine, but we do have a little bit of kind of a sanity check to talk through these derived data sources. But, you know, for data that's collected off of a sensor, we can just report if there's any known reasons why the data would be suspect.
Makes sense. And I think especially for thinking about a tool that was designed with a public audience in mind, being able to act as that kind of expert counsel in a way is important. We do actually have a user who's exploring the tool right now and specifically seeing that we have some layers around specific agricultural crops like corn and soy, but not so much around things like animal agriculture manure. Is there a reason for that, or how are, I guess, even more broadly, how are you thinking about the types of data layers that are available versus not?
That's a great question. In my years on the project, I don't know that we have discussed sources of like animal pollution in that way. We just have the monitors on the watering networks that would potentially get the runoff from some of those operations. All I can say, Shannon, is that based on projects I've been on in the past, it is sometimes difficult to get data from those operations cooperatively because they tend to be private operations that don't necessarily share their data. Although because we are researchers with public institutions, sometimes we get a little bit more leeway there. I don't know if that would be a question of funding for the project, just not having scope for that type of data, or if there's other reasons why it maybe has been discussed and not incorporated. But in general, yes, that would be a very interesting source of, similar to the agricultural practices, potential sources of nitrogen, phosphorus from various sources. But I don't know that we've discussed incorporating that at this point.
Very good. Okay. Unless someone is in the midst of typing up a question, which we will gladly answer live right now, we are going to start wrapping things up. So I think folks, again, Max and Alejandra, thank you both so much for joining today's conversation and for your presentation and sharing your expertise with us. This is really amazing stuff. And so